Welcome everybody. Chem 1007. Just finishing up some things. Like I said, the study guide will cover just new materials. There'll be five multiple choice questions from the new materials and five true and false questions from the new materials. Anyhow, alkali metals, when they're purified, what do they look like? They're not going to show up in nature being pure. We have sodium here that can be cut almost like butter. Amazing, almost looks quite interesting, and it's very reactive with water, we're going to find out, along with all the group 1 metals. There's even more reactive solids from group 1 that are going to react with water even more vigorously. Also, group 1 has greater reactivity than group 2. They do have these metal properties we mentioned in the last video, high luster and brightness, where they reflect light, conductivity, electricity will flow through them. They're found in nature, usually not in their elemental form. We have to purify them. This here was produced by a chemical company, obviously. So moving right along, some unique things. The ionization energy is fairly low, but it is endothermic. You have to put energy in it into the gas phase to get electrons to come off these metals. We're in the gas phase when we talk about ionization energy, not the solid that we just looked at. Atomic radius increases as you go down the column, as you go down the group. Which makes sense. You get more core electrons. The density increases as you go down the column. Of course, you get more nucleons in the nucleus, such as the protons and neutrons. So it makes sense that cesium would be a lot more dense than lithium. The melting points, actually, strangely enough, they go down as cesium has a much lower melting point than lithium. And that's because of the metallic bonding, which is a third type of bonding. We talked about covalent bonding, we talked about ionic bonding, but there's metallic bonding where there's overlap of metal orbitals. Sometimes we see that in transition metals with d orbitals, but we also see that with the group 1 alkali metals. And so unique and interesting, and we know that the electron configuration always has a single electron in the s orbital, and the 2, 3, 4, 5, and 6 reflect the principal quantum number. So alkali metal chemistry, what exactly is that? Well, lithium doesn't hardly react at all with water. But if we throw purified lithium, doesn't hardly react with water. But if we throw pure sodium into water, it's very reactive and exothermic. And potassium puts on quite a show where you get colors and sparks and tons of energy given off. It's exothermic. These are very fun reactions to do. And so we talk about differences in alkali metal chemistry. Lithium can react with O2 gas and form lithium oxide and give you exactly what you expect, a 2- oxide ion. Sodium a metal can react with oxygen gas and form a peroxide, which a little bit lower negative charge on the peroxide, only a -1 per oxygen. And then uniquely, we have a metal such as potassium, rubidium, and cesium further down group 1 that form superoxides, which really have like a half a negative charge on each one. So these metal superoxides are unique compounds, as are sodium peroxide ions. So if you're a synthetic chemist, you like to make different elements, this is the start right here. So flame test, just something that's very qualitative. We don't need fancy equipment. All we need is a Bunsen burner and a few things, and we can test solutions for metals. And the heat acts as kinetic energy to excite the electron to these transition states that then when the heat is taken away, the kinetic energy reduces, and the electron, which was heated, it goes up to here because of the kinetic energy, not because of heat per se, but the heat caused the kinetic energy. And then we get this lowering where a light is emitted. So if we have sodium, we get this yellow light, and we don't have to use flame. We could use electricity to generate kinetic energy as well, or lasers, or even light itself. And so You excite the electron through the kinetic energy of the flame, and it then relaxes, and then the light is given off. And for lithium, it's this nice, pretty red color. Sodium is this beautiful yellow color, and purple giving you this royal color for potassium. The flame test, we could use a visible light spectra to measure this if we wanted to. That makes it a little more sophisticated. But a Bunsen burner and some propane and a solution is often enough. There is what they call this unique blue cobalt glass that can filter out sodium, because sometimes when sodium is mixed with other metals, it can cover up the presence of other metals because it's very bright, very intense, and the bright yellow will block the detection of the visual qualitative presence of other colors. So they use a blue cobalt glass to do this, to see other colors if there are other metals in the solution. You could just use a Bunsen burner, what they call a platinum or a nickel chrome loop, for the solution. Hydrochloric acid to dissolve the metals. So remember, the metals are typically oxides and will dissolve in acids, and therefore when they're completely liquefied in solution, they burn much more readily and enhances the flame color. You can use lithium chloride, sodium chloride, potassium chloride as tests. They're very volatile and give off lots of pretty colors. Cobalt blue glass that filters the sodium, because sodium's all over the place. Tongs or forceps to help keep you safe. Goggles, lab coat, all those things are necessary. And they go through here on something very simple that someone can do if they're interested. Now we're jumping to group 2. Group 2 is not as reactive as group 1 alkali metals. The alkaline earth metals, though, have some other unique properties. They have higher densities. They have higher melting points. Their atomic radius, it's not much different, but just a tad bit bigger. Ionization energy, not that much more, but you're removing 2 electrons instead of 1, so it is a little bit higher. You need more endothermic energy for the gas state. Remember, you're removing electrons. You're doing electron or ion. You're doing ionization energy or electron affinity, all in the gas state of these metals, which we're not used to using these metals in the gas state. So ionization's energy still remain low, not quite as low as the alkali metals of group 1. You form +2 cations instead of +1, losing 2 valence electrons. And you could see 2s, 3s, 4s, 5s, 6s, all in the group 2 in the column of those atoms. Uniquely, beryllium, which is lighter than magnesium, and it's in a lower principal energy row, and it does not react with water. Magnesium only reacts with steam. And then finally, as we go down the group, it gets easier to take an electron because more core electrons are present to shield the protons, and the shielding effect, the effective charge on the valence electrons becomes less and less with more core electrons. Reactivity tends to increase as you go down the group. Electrons are easier to remove because they're further from the nucleus and they more readily react, and they're more shielded and not held as tightly. And so you can see the reaction of calcium. I believe this is pure calcium. Calcium is reactive. Pure calcium is reactive in water. Group 1 elements, thinking about the reactivity, group 1 elements like lithium, sodium, and potassium these elements become more reactive as we go down the column. Of course, group 1 is more reactive than group 2. Atomic size increases as you go down a column, as you go down a group. Atoms become larger because they have more electron shells, they have more core electrons. The outer electron becomes further away from the nucleus, making it easier. Less energy is needed to pull that electron away. There's weaker attraction by the valence electrons to the nucleus because of the core electrons and the electron shielding by the core electrons. Easier ion formation. Losing an electron is much easier, and they react more with water and halogens when they're further down the group or down the column. Reactivity further explained, lithium reacts very slowly with water. Now we're going back to the group 1 elements, but sodium reacts very vigorously. Potassium reacts explosively with water, and rubidium and cesium can ignite and explode. And we don't even want to talk about francium, an artificial element that's hardly found on Earth. Increasing metallic character as you go down the group. So we're jumping to group 6. We skipped a lot of elements per se. I don't know if there was a mistake in the PowerPoints. I double checked it, and no, they jump all the way to group 6. And what happens here is you see that you have 2s2, 2p4, 3s2, 3p4. You have these unfilled p orbitals, 4s2, 4p4. When you start getting into selenium, you get into d electrons, which can have very unique electronic and magnetic properties. Tellurium, polonium, very unique with polonium having d and f orbitals, tellurium and selenium having d orbitals, which can be very interesting for chemistry and even coordinated compounds that we'll talk about in Gen Chem 2. So the melting point is very, very high for oxygen, or excuse me, very, very low for oxygen. And then the melting point goes up when polonium is like, 450 for tellurium, 250 for polonium. So it's not, the trend is a little bit jagged. It's not a complete straight line. Density goes up as you go down the column, as you would expect. You get more protons and neutrons in the nucleus, so the density, of course, should go up. The atomic radius increases as you go down the column, as you would expect. And the ionization energy uniquely decreases because it gets much easier to pull an electron off something that's in the maybe it be the sixth row. Core electrons do a lot of shielding, so the energy needed to pull an electron away in the gaseous stage for polonium is much easier. And so polonium is actually radioactive. We don't really want to work with that too much. Tellurium is considered a metalloid like silicon, but it's much bigger. And oxygen tends to oxygen tends to gain 2 electrons, as does sulfur tends to gain 2 electrons. So it shifted from losing electrons in group 1 and 2 to where group 6 clearly wants to gain electrons. Where if we talk about group 5 and group 4, those, tend to gain electrons, but group 6 definitely has a high electron affinity and a high electronegativity, especially with the upper class members of that column, which is oxygen and sulfur. So electron configuration, thinking about hydrogen. Hydrogen is so cool. We can make hydrogen gases. We did in labs this semester, and hydrogen is much less dense than air. The density is way lower for hydrogen gas than air, and lower than oxygen, in fact. And in the presence of water, we can make H+, which is an acid, which is important in acid-base chemistry, which biochemistry uses extensively for us to live and survive. And hydrogen, when it's can react with metals, and it can gain electrons. We saw that with hydrochloric acid reacting with zinc metal, and hydrochloric acid being hydrogen gas being formed from that zinc metal. So hydrogen is also part of the activity series, and it acts like a metal in many ways. Oxygen, uniquely O2, it's what we need to live on. It's colorless to us. It's diatomic. Oxygen also does exist in other forms. Most commonly ozone, which is very high up in the atmosphere and protects us from UV light. It's also a disinfectant, but it's also toxic and can be poisonous in high concentrations. You cool it down, you get this really beautiful pale blue color. It has a sharp odor. Ions can be formed of oxides, such as 2-, and then peroxide, which is O2, which is 2-, and a -1 charge on every oxygen. And then a superoxide, which really has like a half a negative charge on 2 oxygens. So less charge as we go through that series. Oxides, peroxides, and superoxides have unique chemical reactivity. Halogens are really cool. They're group 7. They love to gain electrons. Their electron affinity is very exothermic, and it loves to do that, especially fluorine. Really attracts electrons like it's nobody's business. It has a super high electron affinity. Its ionization energy, though, is really high and endothermic, unlike its electron affinity, which is exothermic. And the ionization energy is very high for fluorine. It doesn't want to give up any of its electrons. It has the highest ionization energy for or should I say, period 2 elements. And it has a electron configuration, as all of these do, with two electrons in the s orbital and 5 electrons in the p orbital. So it just needs one more electron to fulfill its octet rule, and it does the same with bromine and iodine, although 4d orbitals become present in iodine, and bromine, of course, has more core electrons than chlorine or fluorine. The melting point is actually super low for fluorine and chlorine. Bromine, it's going up a little bit more, and then iodine has a somewhat high melting point up there with water. And density, of course, increases as these atoms get bigger and more core electrons get added. You get more protons and neutrons, so the density is going to go up, as you would expect. The atomic radius is going to go up in angstroms, as you would expect. And the ionization energy actually goes down, as you would expect, because it gets easier and easier and easier to pull an electron from a bigger and bigger atom that has more core electrons, shielding the valence electrons, which will be ripped away from the charge on the protons, which attract the valence electrons, unless the core electrons, of course, get in the way and provide that shielding effect. So halogens are considered nonmetals. They have a high negative electron affinity and exist as anions in nature. You don't find pure fluorine, you find fluoride with a negative charge. They react directly with metals if they're purified to form metal halides, such as potassium iodine, things like that. So the ionic compounds can be made. Noble gases, very large ionization energy because they have a full electron shell. They don't want to form cations. They don't want to form anions. Their electron affinities are positive. So if you want to give them an electron, you're going to have to put in energy. And if you want to ionize them, you got to put in energy. So you have to put in energy no matter what you do. So they're very non-reactive. And therefore, there often can be monatomic gases where they don't even need to be diatomic. Argon is present in our atmosphere at very high concentrations relative to other gases, and it's very non-reactive. And you can use these gases as a background media for other reactions. And so I thank you. This is the last of chapter 7. Please watch, enjoy. And Chem 1007, thank you for a great semester. I'll see you in class.